Well, good morning, everybody. Thank you for joining us for our webinar on visualizing isosurfaces of higher order elements. Today, we are going to be presenting some research that we've been doing on this subject that's also been communicated at the AIAA SciTech conference. So we do have some white papers available for you to take a look at as well. Our presenters today are going to be Dr. Scott Imlay. He is our Chief Technical Officer and has been the principal researcher on this project. And myself, Scott Fowler, I'm the Product Manager of Tecplot 360. I'm going to be available to answer questions. So we do ask that you participate in this webinar by asking questions during the webinar. So with that, I'll pass it over to Dr. Scott Imlay to present the research that we've been doing on the subject of visualizing higher order elements.
Thanks, Scott. The agenda today is we'll be covering the what and the why of higher order elements and talk about the recursive subcell refinement technique we use for finding isosurfaces as well as the curved surfaces in 2D surfaces, and talk about some results in future work. This is preliminary research on adding higher order element visualization to Tecplot. So the goal is, in the long run, is to get it into Tecplot. This is preliminary, however. Sorry about that. There we go. So what are higher order elements? Most finite element methods assume a linear variation of the solution across element edges. Higher order elements assume a nonlinear distribution across the element. Usually it's quadratic or higher order polynomial, and sometimes the element geometry is curved. And to be a higher order method, it needs to be higher than second order accuracy. Here's a couple of examples of higher order elements. The one on the left is a prism. The one on the right is a pyramid. We also have tetrahedra and hexahedra. You can see the distinctive character of these Lagrangian elements is that they have additional nodes. Looking at the prism, for instance, would normally have 6 nodes at the black colored spheres at the corners. But in this case, you have the additional nodes on the edges and the face centers to give you 18 nodes total. Likewise, in the pyramid, you would have 5 nodes at the corners for a linear element, but we have the additional nodes at the face center and at the edge centers to give you 14 nodes total. With the tetrahedra, it's 10 nodes total, and the hexahedra actually has 27 total nodes, which includes 1 in the cell center. Why higher order elements? Well, they have better accuracy or less cost for certain problems. This specifically, that's true for unsteady flows and vortical flows, those flows containing vortices. The image on the right is an example of a vortical flow, both unsteady and vortical actually. It is a wind turbine, and you can see it has a wingtip vortex or a blade tip vortex coming off of the blade, and it interacts with vortices shedding from the pylon in a complex way. So this sort of calculation could be done with linear elements, but it would take millions, perhaps billions of elements to get an accurate solution. Whereas you can get away with far fewer elements in with higher order methods. This calculation was actually done with fourth order differencing in the wake region, so it is higher order. Why higher order elements? Well, this is another example of aeroacoustics. Aeroacoustics, you can see the image in the lower right are the pressure waves coming out of a nozzle. Because you have these high frequency pressure waves, it benefits from the higher order of the elements. If the image on the upper right shows what happens if you treated this the elements as linear by throwing away the extra nodes for the purpose of visualization. So it's the same solution, but you've just thrown away the extra nodes and used it in a visualization code like Tecplot. And you can see that it doesn't give you, doesn't really represent the true solution. So this is the motivation for us to actually add higher order visualization to our products. Final motivation comes from the NASA CFD 2030 vision document. In this document, they say, quote, higher order methods will likely increase in utilization during this time frame, although currently the ability to visualize results from higher order simulations is highly inadequate. So others have seen this as a problem, and that's another reason we're trying to address the problem. What are the challenges? Well, first is you must be able to read the higher order data from common file formats. CGNS, for instance, has a higher order element capability. VTU is another file format. There are others. Second, you need the internal data structures within your code to be modified to handle the additional nodal data or connectivity data. It has to be performant for visualization without excessive subdivision. I'll explain the subdivision part more in a minute. Most algorithms, the underlying algorithms, I should say, most algorithms currently only work with linear elements. So for example, algorithms for generating contours, slices, and isosurfaces assume extrema at the corner nodes. An example would be marching cubes, if you're familiar with that. And that's just simply not true for nonlinear elements. You may have extrema anywhere within the element. Could be somewhere in the middle of the element, could be on a face or on an edge. So you can't count on it being at one of the corners. Also, the streamlines, streak lines, and particle paths algorithms need to interpolate using the higher order basis functions. And element edges and surfaces and meshes and shaded surfaces may need to be curved. Generally, they're just straight. The edges are straight. So how do higher order elements work? Well, the underlying function is computed using basis functions. So the phi in this equation at the top are the basis functions, the n basis functions. And you get your solution as a linear combination of those basis functions, where the Ci are the coefficients in the linear combination. So the solution variation over the domain is a linear combination of the basis functions. If the closed coefficients, the Ci, are equal to Ui, the values of the solution at node I, then your basis functions are nodal Lagrangian basis functions. And that's what we are dealing with currently. In all but pyramids, these basis functions are polynomials. But for pyramids, they are rational polynomials. That is needed because you need the solution to match at the faces between a pyramid and a tetrahedra, for example. And the only way to do that is to modify your basis functions. And that's as far as I'll go in the underlying basis function discussion. If you want to know more about the basis functions we're using, we do have the white papers that Scott Fowler mentioned, and you feel free to download those white papers and ask any questions. Send me email for questions if you have any. So how do we do the isosurfaces in higher order? Our goal is to visualize the higher order element isosurface using existing underlying algorithms for the linear elements. So Tecplot has existing algorithms, and we want to take advantage of those at the lowest level. The general subdivision technique that we use creates a set of linear elements that represents the variation of the solution across nonlinear elements. So how this works is you subdivide the higher order element into sub-elements. And then you subdivide the new sub-elements into smaller sub-elements, interpolating to the newly created nodes using the original higher order basis function. That's key. And then you repeat the subdivision until the desired accuracy is reached, treating the smallest sub-elements as linear elements in the final visualization step. Tecplot uses selective subdivision to reduce memory usage and computational cost. So in this case, we subdivide only those cells that may contain the isosurface with some buffer to handle the fact that the extrema may be within the cell. And we discard the unneeded sub-elements as the subdivision progresses. So in the end, you only have those sub-elements that contain the isosurface. So it's a big savings in terms of memory and computational cost. And I'll give you some examples. This is a brick or a hexahedral element, 27 nodes. And then the quadratic hexahedra subdivides into 8 subhexahedra. Additional subdivision is done by adding nodes at the edges of the subhexahedra, and then you interpolate to the new nodes using the hexa 27 quadratic basis function. So that way, and then you can just repeat this as necessary to get the desired level of accuracy. Likewise, for the tetrahedra, the quadratic tetrahedra also subdivides into 8 sub-tetrahedra, as you can see in the right. And then additional subdivision is done by adding nodes at the edges of the subtetrahedra. And you interpolate again to those new nodes using the quadratic basis function. That's the key in all of these element types, is you use the main element higher order basis functions. You can see a pattern here. The pattern is that we subdivide into smaller elements. In this case, with the prism, we subdivide it into 8 prisms. And each of those subprisms can be divided into 3 subtets. So this is how this is different than the previous two, where the hexahedra is subdivided into hexahedra and the tets subdivided into tets. In this case, the prism subdivides into 24 subtets. And then on each additional level of subdivision, we deal only with tets. So each of those subtets can be further subdivided into 8 sub-subtets. And again, you interpolate using the overall, in this case, Prism 18 quadratic basis functions, and repeat the subdivision as necessary. Very similar to the Prism for the pyramid. You get 16 tets total from the original pyramid subdivision. You can see how you're on the right, you're originally subdividing into a set of pyramids and tetrahedra, and each pyramid is can be subdivided into 2 tets to give you a total of 16. And on subsequent subdivisions, we interpolate to new nodes using the Pira of 14 quadratic basis function. So those are the 4 fundamental elements that we support in our and within Tecplot. So this is how we currently have it implemented. And as I mentioned at the beginning, this is preliminary work. So we currently have it implemented as an add-on to Tecplot 360. In this add-on, the additional nodes in the higher order connectivity are stored in cell-centered or bi-element variables. So for example, the tetrahedra has linear tetrahedra has 4 nodes in its connectivity list. It specifies the node numbers of 4 nodes at the corners. The additional nodes in this case are stored in these cell-centered variables. So the edge nodes are stored in the cell-centered variables. Until the final recursion, sub-element exclusion uses a heuristic buffer on a test of solution range within the cell. So we could have an extrema within the cell. So when we are deciding, can this element, or this tet, for example, or subtet, could it possibly contain a piece of the isosurface? We have to give a little buffer. So that we don't unintentionally discard an element that we will need later on in the subdivision process. We currently use visual examination of the isosurface smoothness to determine adequate subdivision accuracy. We'd like to automate this in the long run, but at this point, you just run it and look at it, and if you need more, you run it with more subdivisions. And finally, Tecplot's standard linear trilinear isosurface algorithm is used. This is an example result. And this is a case with prisms. And it's a simple function, which is just the distance from a point in space, as shown there. So it's a sphere. The exact isosurface would be a sphere. And this only uses 2,353 subtets because of the selective subdivision. If we had not used selective subdivision, it would be 663,000 subtets. So that's about a 2 orders of magnitude saving in terms of memory, and also savings in computational cost. Same function, in this case with pyramid, is shown here. So as I mentioned earlier, the pyramids subdivide into tets. So you can see on the right the actual set of subtets that are retained for this isosurface. And you can see how they're clustered around right around the isosurface. It's the same isosurface. In this case, we use only 3,800 subtets, whereas if we had not used selective subdivision, it'd be 1.3 million subtets. So again, a 2 orders of magnitude reduction in the number of subtets and memory usage, and corresponding improvement in performance. Final result I'd like to show you is for surfaces. In this case, it's a quadratic surface, triangles in this case, quadratic triangles. For the leading edge of the Onera M6 wing. The image on the left is what you would get if you threw out the additional nodes, the edge-centered nodes, and just treated them as linear elements. And you can see it's a pretty coarse representation of the leading edge. On the right is what you get after 3 levels of refinement. It's much smoother. Now, in this case, we do not use selective refinement because for the surface, you need all of your elements. But it's also, you tend to have far fewer surface elements than you have volume elements to begin with. So that's not a significant problem, not as significant as a problem as it is with volume elements. So where are we going? Well, we would like to apply the recursive isosurface approach to elements of cubic or higher order. We know a lot of people are doing cubic elements, and we know of people who are doing higher order. So that's something that we will need to do in the near future. Most immediately, we're working on streamlines and particle paths generated using higher order element basis functions. So that is our near-term future development. Now, we do have the add-on that I mentioned, and we are looking for partners to try out our prototype add-on or to provide data for testing. So if you are interested, please feel free to contact myself at the email shown there, scottimlay@tecplot.com, or Scott Fowler at tecplot.com. And I'm going to pass it over to Scott Fowler at this point.
Well, Scott, thanks for the presentation. And we'll get to your questions here in a second, but first we'll pitch our next webinar, which is Back to the Basics. So we go from a very technical subject of higher order elements back to the basics of using Tecplot 360. That is going to be presented by account manager Jared McGarry, and he's going to be assisted by our product owner, Devin Simpson. So the two of them will be presenting this webinar March 24th, 10 a.m. Pacific. Okay, so let's go to the next slide and talk about questions. And we'll also tell you about where to get various tutorial videos, training, and support. We do have support available on, we're located on the Pacific Coast. We're available 6:30 a.m. to 5 p.m. Pacific. We do have support in Europe and Western Asia available at the email address that you see there. And then if you are outside of either of those two regionalities, your first line of defense is always going to be your local distributor, which you can find there. So with that, let's go into some of the questions. I answered a number of them already, but then there are some that are a bit outside of my level of expertise that we'll have to pass on to Scott Imlay. But let's go with one that I partially answered. Is there support for Tecplot file formats planned? And Scott Imlay, what I answered here is that we don't have definite plans for supporting HOE and Tecplot file formats, and that we're starting by using the CGNS standard. Do you want to add anything to that as far as the Tecplot PLT formats, Scott?
Yeah, I think that's the best way to look at it. We do have kind of our temporary approach to how we're handling it in our Tecplot format is, as I showed on the on that one slide about our implementation, where we treat the extra nodes as cell-centered variables. If you really wanted to, you could write in that format. We don't guarantee that we will continue supporting that in the future, though. So that would be a temporary thing. If it might be, if you just want to try the prototype, it might be an easier way to do it in the short term, but yeah, don't depend on that in the long run. I think, I don't know, do you have any other thoughts, Scott?
No, not at the moment. Just a reminder that this is a research project, and it is like Scott showed, we are implementing this as a Tecplot add-on at the moment. So an add-on is a plug-in to Tecplot 360, and it's functional for showing the isosurfaces and the surface data. And again, we're looking for people to collaborate with us, because we do believe that higher order elements have been certainly gaining steam, and something that we think the industry is going to need. So we want to continue this research with partners. Another question here, Scott Imlay, is the assumption that we have isoparametric nodal data?
That we have isoparametric nodal data. So I'm struggling a bit with isoparametric. No, okay, I'm sorry. So you're asking, is the assumption that we allow curved elements of the same order as the basis function for the solution, which would be isoparametric. We actually currently do that, but you don't have to do that. In the long run, our goal is to not require isoparametric, and we know that some people are doing basically linear geometry and higher order basis functions for the solution. Sometimes they actually have higher order basis functions for the geometry than they have for the solution. So it can go either way, and we would like to support that. But in the add-on, actually, it is at this point isoparametric. And if you just wanted to do linear, yeah, I mean, to take advantage, to create a linear element, in this case, you just have to make sure you put their edge center nodes in a location that gives you a linear element.
Okay.
Hopefully that answers the question.
Another question here regarding GMesh. If you're familiar with the GMesh algorithm for plotting higher order solutions, can you comment on how our algorithm relates, similar or different to the one in GMesh?
I'm not super familiar with how GMesh does it. So my understanding that it is that it also does a subdivision technique, but that it does not do it selectively for the isosurfaces. I think I should leave it there, because I don't want to state that I know more about GMesh than I do.
It sounds like maybe a little bit of research on our side into GMesh to help answer that question more fully would be useful.
Yeah.
Okay, another one here about Bezier representation. Did you consider using a Bezier representation rather than a heuristic buffer approach to make sure not to include extrema that cannot be seen via the nodal data itself?
That is a very good idea. We have thought about it, but we have not gone any farther than thinking about it. It's true that if you were to use Bezier representation, then they wouldn't be nodal values anymore, but they would be the I forget the exact term, but there's points in space that are used to adjust the shape of a B-spline, for instance, and those are the minima and the maxima are at those points, and so that way we could guarantee it. Now, most of our customers are not using that as their basis functions, though, at least the customers we've talked to. And so we would have to find a way to convert from more common basis functions to that before. Yeah, I mean, those are some of the issues that we thought about. If any of you are using those as your basis functions for not just the geometry, but for your solution data, I would really like to hear from you and learn more about it.
Looks like we have a couple more questions here, Scott. How does the presence of higher level elements, or maybe that's higher order elements, affect interpolations onto a different grid in terms of fidelity and cost?
So for fidelity, obviously it would use, I should say, first let me start. The add-on does not currently change the interpolations within Tecplot. So if you were to interpolate to another grid, it wouldn't take advantage of that at this time. But in the long run, we certainly intend to do that. So talking now about the future, what you would do is utilize the underlying basis functions exactly. So you would get your interpolation to any new nodes would be based on the higher order basis functions. So in terms of fidelity, I guess I think that would mean it has the same fidelity as the higher order solution. Sorry, I had an audio connection lost for a second there. I hope you heard me. So the second part of your question is cost, and the cost is going to be higher, but in general, higher per cell, because it has to do a solution of a nonlinear system of equations, especially if you have nonlinear geometry. It will have to solve a system of nonlinear equations to do the interpolation. But you have far fewer elements generally in a higher order mesh than you do in a linear mesh. And so that means you can, it's hard to do to be sure, but it's quite possible that it would be cheaper overall than if you're just going from a linear mesh to your new mesh. That's it's hard to tell for sure, but that's my guess at this point.
Thanks, Scott. And then final question here is, how does Tecplot know the basis functions that are used for the higher order solution? Does Tecplot expect solutions to be converted? Another question came in. Sorry, let me repeat this. How does Tecplot know the basis functions used for the higher order solution? Does Tecplot expect solutions to be converted to a predefined format?
Yeah, at this point, we really only support the CGNS format, quadratic elements, the Lagrangian or quadratic elements, or that modification of the Tecplot format that I mentioned earlier. So yeah, if you've, for instance, converted into CGNS, then when it will have the element type for each of the zones, and when we read that CGNS file, that's how we know.
Okay, so the basis functions are then defined effectively by the file format and element type.
Right, yeah.
Okay, well, that looks like it's it for all the questions. So thank you for all your attention today. And again, I'll just put a plug in for, this is an active research project. We think that this is an important capability to add to Tecplot 360. And again, it's research code. And we're looking for additional partners. Scott Imlay has met with quite a number of people doing higher order element research and writing higher order element codes over the last, well, hard in this last year, but certainly the last time SciTech was live and in person. We had a lot of really good meetings and would like to increase the number of people that we are connected with in this community and doing this research. So please do contact Scott Imlay. Again, his email address is scottimlay@tecplot.com, or you can contact myself, Scott Fowler, at tecplot.com, and we'll be happy to share more thoughts and share the research add-on with you to help move this work forward. Scott, any parting thoughts?
No, not really. Just thank you for attending. I really appreciate it, and yeah, feel free to shoot me an email if you have any questions or if you have any ideas. Appreciate it.
Okay. Bye-bye. Have a good day, everybody.
Thank you.